I'm very happy and very honored to be introducing Roseanne DeStefano today. Um, Roseanne received her PhD from Stony Brook, working in field theory, working in supersymmetry and related issues. But then she decided to work on something hard, realizing that the true excitement in this world is doing astrophysics. So she came up to CFA in 1992, where she's been ever since. Recently, she's been focused on exoplanets or extroplanets, as you'll be hearing today, but she's also got sort of broad interests in triple systems, in binary self-lensings, and that can be applied to binary AGB stars or binary compact objects. What you might be hearing here is just a very broad range of interests, starting from field theory and then moving into various X-ray systems and now triple systems and now exoplanets. So what I'd really like to say here is, on a personal note, that I'd like to highlight something about Roseanne, and this is really going out to the postdocs and early career community, the students. Roseanne's got very broad interests, and they cover both theory and observations. And they're not limited to a specific bandpass or a type of systems. So if you find yourself with a curious observation or a theory question that's bothering you, like I had one of, what would it be like to be in a galaxy where a supermassive black hole merger occurred? What impact would the merger have on the galaxy? And she and I got to chatting about it, and the answer seems to be, in all likelihood, probably not a huge amount, but there might be something going on there. So what I'd say is that if you've got this kind of question, I'd highly recommend having a conversation with Roseanne, either before or after a colloquium or a gathering. Now, unfortunately, with COVID, we can't do that so easily, but email and Zoom work. And I find that she can really often provide a useful pointer or a name, or who knows, maybe even a collaboration. So along those lines, I'll finish by saying that she's also been preparing for the imminent opening of the very exciting Vera Rubin Observatory's LSST. And she'd love to discuss that with others who are here or elsewhere. So if you've been wondering about how you might be able to use that, why don't you send her an email and see if you can set up a chat. She's always fun to talk with. So with that, I will let her take the baton and tell us all about the first candidate planet in an external galaxy.
Thank you very much. Okay, I'm going to start by showing you the wonderful team that did the research that I'm about to tell you about. This team is, or at least members of it, will be doing a group presentation next Wednesday at the High Energy Astrophysics Division seminar, where we'll be able to tell you not only what the result is, but how we did it, and specifically how they did it. So that should be an exciting talk next week, and it can, be used to answer some of the questions we may not have time for today. So today I will start with a very brief overview of external galaxies and X-ray binaries before telling you how to find a planet orbiting an X-ray binary. And then I'll tell you about the research that we did to find a planet candidate in the galaxy M51. So as long as humans have been able to look up at the sky, they have seen stars. And they have also seen this continuous band of stuff whose nature was a mystery. That mystery was solved, at least in good part, in 1609, 1610 by Galileo, who wrote in Sidereus Nuncius, his account of the first few months of his telescopic observations, that when he looked at the Milky Way, to whatever region you direct your spyglass, an immense number of stars immediately offer themselves to view, of which many appear very large, but the multitude of small ones is truly unfathomable. And we know that to be true from much deeper observations today. Now, even after Galileo, there were still some puzzles about nebulae. So there were small nebulae that were scattered around the sky, primarily out of the plane of the Milky Way. And by about 1750, it was being conjectured that perhaps these were similar to our own Milky Way, but just farther away. So they were considered as potential island universes. Now, humans, we do that, right? We see something close to us, and then we see something that could be like it, and we wonder, is that similar to what we know? And we did it again, or even earlier, with stars, thinking that since stars seem to be similar to the sun, perhaps they host planetary systems as well. And, the apparently unexceptional nature of the sun suggests that the answer to whether other stars host planets is yes. But tremendous technical advances were needed to find extrasolar planets. And our own Dave Latham has played a very key role, in particular with his discovery or not discovery of the system, but his study of the system in 1988 with his team of HD 114762b. Now, the first planets to generally be recognized as confirmed were kind of surprises, right? Because they were planets orbiting pulsars, and not just any pulsar, but fast spinning pulsars, pulsars that were spinning at rates close to milliseconds. So how does this happen? Well, we don't really know the full answer to how the planets form, but we do know that there is a model for millisecond pulsars that has some observational confirmation, in which the neutron star has a companion that donates mass, and as mass falls onto the neutron star, it spins it up. And so we expect that type of process to take place. And we've seen examples of systems that do, that both have been seen as X-ray binaries and as fast spinning pulsars. Interactions among neutron stars and other stars are perhaps most common in globular clusters. Here we see at the location of that green open circle, the position of a millisecond pulsar. And this is the artist's conception, with the pulsar being that kind of small, bright thing in the middle that has jets. That's what marks it out as a pulsar. And the thing next to it is a white dwarf. That white dwarf is presumably the remnant of the donor star that gave mass to the pulsar and spun it up. This picture, however, is dominated by this huge thing on top, which is none other than a 2.5 Jupiter mass planet orbiting this system at 23 AU. And it is thought that this planet was in orbit during the time when the X-ray binary was active. So it would have at one time been an example of a planet orbiting an X-ray binary. So what are X-ray binaries? Well, we have a lot of experts on this here. We're just talking about a system in which a compact object, white dwarf, neutron star, black hole, is accreting matter from a companion. Let us count the ways. Not really, there are too many ways. You can have any of these types of accretors. You can have a donor star of any mass at any state of evolution. It might fill its Roche lobe, it might not. But these are among the most fascinating systems in the universe. Now, this is just an artist's conception, but you can probably convince yourself, if you look at it as much as I have, that there are irregularities. And in fact, given the high rate of mass transfer, the amount of mass that is accumulating in a relatively small space, there can often be irregularities. In particular, there can be clouds of gas and dust, sometimes associated with the disk and sometimes not. When a cloud of gas and dust happens to pass in front of the X-ray source, the X-rays interact with it, and they change, that interaction changes the spectrum of the X-rays. This is an example of a system in which this is happening, and it's happening on a regular basis. This is called a dipper, or a dipping source. We think these are that clouds of gas and dust are passing in front of the X-ray source. producing here these irregular dips in the count rate. And at the same time, they produce changes in the hardness ratio, the ratio of harder photons to the total number of photons in this case. In fact, Josh Brindley was a co-author on this particular paper. So I could tell you some more things about dippers, even regarding planets, but let's leave that to the end if we have some time. The key thing I'd like you to take away from this is that the hardness ratio, which is a proxy for the X-ray spectrum in this case, is changing as the dip begins, as it progresses, and as it stops. And that's very characteristic of these types of events, which have been studied since at least the mid-1980s. And now, this is one of the hearts of this talk, okay? Same picture. But what I'm going to say now is something that Nia Amara and I recognized in 2018. And that is that the size of the X-ray source, the region that's emitting X-rays in many X-ray binaries, is small. It's comparable to the size of planets. So that means that if a planet happens to pass in front of the X-ray source, it can cause a near total or even total eclipse that lasts for a short time. And this was our theory paper in 2018. And later on, I decided that perhaps we could look for them. Before telling you about that, let me just show you these wonderful images that are associated with our own Andrew Vanderberg's paper from 2020, in which he discovered a planet orbiting a white dwarf. And here again, it's the artist's conception, but you can see that the planet is bigger than the white dwarf. And that comes from their paper. So if this white dwarf were post-nova, or if it were burning material, as happens in super soft X-ray sources, it could be totally eclipsed by its planet. So this simple observation that Nia and I made opens up a new field of exploration, and it doesn't require any new technology. What we do have to do is to extract existing data from the archives and analyze that data and model anything that looks like a transit, and also model all possible other models, make sure that we've considered everything so that we can identify false positives. So this sounds like looking for a needle in a haystack. But for those of us who've been in astronomy before, for a while, we've heard about this before. This is what Charles and his colleagues were doing in the early 90s. And I'm giving you now the example of microlensing, where they were looking for unusual events in which the amount of light we receive rises and then falls. And there were many thousands of types of variability that did that, but they were looking for the specific examples of microlensing. And this particular light curve is a very special one. This event was discovered by a Japanese amateur who was looking for novae, and he found an increase in the light from a system that was different from what he was expecting. He alerted the world, and it turned out to be a very, for at that time, one of the best studied microlensing events. In fact, the source star is only about a kiloparsec away, and we can look at its spectrum. Einstein's theory predicts that the spectrum shouldn't change, and it didn't. So we recognize microlensing events by the light curve shape, and we also recognize them through spectral changes or the lack thereof. Transits of X-ray sources by planets are also identified by their shape, as quantified by a fit to the light curve, and by the lack of spectral changes. Because after all, when an object passes in front of an X-ray source, and that object is, has the characteristics of something with a well-defined surface and it's optically thick, there's no reason for the X-ray spectrum to change. So now this is the second key secret no longer a secret, to how we can search for planets in external galaxies. Not only can we look for dips in X-ray sources, but seeing them in external galaxies makes it possible for us to resolve many different X-ray sources in single looks, single observations with either Chandra or XMM Newton. So on the right-hand side, you see in purple some emission from hot gas emitting X-rays, but the point-like sources are mostly X-ray binaries. And so the great thing is that we can resolve them. I like to think of these X-ray binaries in external galaxies like the Shakespeares of their galaxy, or the Newtons, the Galileos, right? They are maybe dozens to hundreds of sources that out of the 100 billion in the whole galaxy shine brightly enough that we can recognize them as individuals from great distances. That makes it possible for us to analyze the light curves of all of these separately and look for dips. This is quite different from the challenges we would face if we were trying to use standard methods at optical wavelengths. So on the left, you see the galaxy, and this is indeed M51. This is often called A, and this is often called B. You see it at optical and infrared wavelengths. So we know that you need good precision to identify planetary transits or radial velocity variations in local stars to find evidence of planets. But if the system we're studying is thousands of times farther away, we get millions of times fewer photons. In addition, blending is a real problem. And so in any small region that you look at, there are many sources, many of which contribute their own kind of variability. So we actually have a relatively easy job doing this in X-rays. So what did we do? Well, we were fortunate enough that Ryan Urquhart, one of our collaborators, had already extracted light curves from 3 galaxies, M51, M101, M104. And each one contained dozens of X-ray sources. Each X-ray source had been observed multiple times. And so we had a large number, about 2,600 light curves to study. And we did. We've also used XMM data, by the way. I want to make that clear as we proceed. We won't have much time to talk about that, but I just want to mention it. So this shows you examples of some of the brightest of the 2,600 light curves that we studied. These particular sources were selected for our study because each had been seen at a luminosity above 10 to the 37 ergs per second at least once, and all of the observations that we used lasted longer than 5 kiloseconds. What did we find? Well, we had to conduct a search, right? The search had very simple requirements. And actually, the story of this is pretty interesting. And I think Julia will probably be telling us a little bit about this next week, because we did all kinds of things to search for events. In the end, a simple algorithm gave us the ability to quantify what we found. So we required that during at least 1 kilosecond interval, the count rate was consistent with 0, and that there was a baseline from which the count rate fell and to which it returned. So that was it, very simple. And we applied that to all of the data, and we found one source, one part of one light curve of one source that obeyed that. And here it is shown in pink. This was a source that is M51 ULS1. It's ultraluminous, meaning that its luminosity is greater than 10 to the 39 ergs per second at X-ray wavelengths. It's soft, meaning that it has a thermal spectrum with a value of KT around 0.1 keV. And so given that, we can compute the effective radius, and we see that it's roughly 2.5 times 10 to the 9 centimeters smaller than the radius of Jupiter. Where is this system? Well, it's in a place where we expect there to be young, massive stars. It's in an inner spiral arm near the center of M51, and it's on the edge of a star-forming region. In 2006, Terashima et al. Used HST data to identify a very likely counterpart, which seems to be, it has the characteristics of a blue supergiant. Now, there's some uncertainty always about that, right? Because you don't know for sure that all of the light is coming from one thing. Light from an accretion disk could also be implicated here. But a blue supergiant is the type of star you would expect in this type of X-ray binary. There's some prior work by Rappaport et al. That shows that. Okay, so now we know what the system is. By the way, we don't know whether it's a neutron star or black hole accretor, but it does seem to be a high mass X-ray binary in which the donor star is of relatively high mass. And so now we have to ask ourselves, what causes the decline from baseline and the rise back up to baseline? Well, we actually stopped work on this for quite a while because our collaborator Ryan and his thesis supervisor Roberto Soria had in 2016 published this event, and they called it an X-ray dip. So in other words, what they were identifying it with was the kind of thing where gas and dust passes in front of the X-ray source. And so my feeling is that these X-ray experts said that, let's just leave this alone and move on. But in fact, what they told us is that this is a very unusual dip, and they weren't quite sure what to do with it. They wanted to make sure it was published, it was out there, people knew about it, but that it was worthwhile to study it further and to find out whether it has the spectral characteristics that you would expect from an accretion-related dip, and how does the light curve compare with other things. So now remember, with an accretion-related dip, we're expecting a spectral change. So what we did is we studied dipping sources from our set of galaxy X-ray sources. Here's an example of one. And you can see that here we're looking at the count rate, which declines to a minimum and then comes back up again. There's also variability here. And I think it's clearest to look for spectral changes in this bottom panel, where again, we're looking at hardness ratios. And we can see that, especially if you're looking at 32 photons in sequence to compute the hardness ratio, you see definite changes as you go into the dip and again, as you come out. What about M51 ULS1? Well, this is the dip, and this is the equivalent image of showing the hardness ratio. And you can see that on the way in and on the way out, there really doesn't appear to be a change. And any changes that we see in this region are comparable to changes we see elsewhere in the light curve. So there was no unusual spectral activity or spectral change associated with this. And the value of KT is the same on both sides of the event. So this does not seem to be a good candidate for an accretion-related dip. What about intrinsic variability? Well, it would be a very unusual type of variability. In this case, because there was no spectral change, but there was a luminosity change and it's a thermal source, what would have had to happen is that the radius would have had to change by a factor of about 3 without changing temperature. And within 3 hours, it would go down and come back up again. So that sounds like a pulsator, but there's no evidence of pulsations in this source or indeed in any sources like it. So intrinsic variability would certainly be remarkable. There'd be a lot to understand about it, but we don't really think that it's that. So what we did is we modeled it as if it were a transit. And this is work done by Vinay Kashyap. So we took a disk, which was considered to be an X-ray emitter, and we took another disk, which was opaque, and passed the opaque disk in front of the X-ray emitting disk, and then saw whether or not we could essentially reproduce this event. And what we found is that this is a key thing here. The size of the eclipser is about 74% the size of Jupiter. Now, I want to point something out to you from the dip. When you see this dip, you may not think, as I know I did not think when I first saw it, hey, transit, right? Because we know when we look at all of the papers on X-ray transits, since many of us read these papers, go to talks, we're used to them being sharper, right? But this shape, as Dave Latham pointed out to me within 30 seconds of seeing it, is characteristic of having an eclipser and a source that are roughly the same size. So in this case, the fit shows us that the eclipser is about 74% times the radius of Jupiter. And that means that it's remember, this source is smaller than Jupiter, right? And the relative speed between the source and the transitor was about 17 kilometers per second. So that's these three quantities. B is the distance of closest approach. This shows us the distribution, the probability distribution of radii. The peak or the mode is over here, slightly smaller than the radius of Saturn and larger than the radius of Neptune. For comparison, we see here some transiting hot Jupiters, and we see here at the low probability end of the probability distribution a brown dwarf, a young brown dwarf. Now, there's something else about the fit, and that is that the only way a large object can give an event like this is if it has a very special distance of closest approach. Because if it were coming sort of straight on, you wouldn't see the kind of dip that we do see. It has to come from farther away. And in fact, the distance of closest approach, B, has to be finely tuned to the radius for large radii. So that's a kind of a low entropy explanation for this event. And that also means that it's not a favored explanation for the event. Okay, there we go. And the small relative speed, well, now we have to be careful here because what we would like to do with the relative speed is to learn something about the orbit, right? But given the relative speed, the size of the orbit really depends on the total binary mass. So we scale to that. But it also depends on the binary mass ratio, the binary orbital phase, and the eccentricity of the planetary orbit. We are looking at this more carefully now as a three-body problem with Sylvia Chunin and Flor Broekgarden, one of our own students, is beginning work on this. And so we really want to get a full three-body solution. In our initial work, we found that solutions were wide enough to be consistent with orbital stability. So that's potentially an important thing. And again, without knowing the exact distance from the binary, we can't say exactly what the flux of incident radiation is. If this is tens of AU, the flux would be comparable to what a hot Jupiter receives. If it is either much closer now or was much closer in the past, the atmosphere could very likely have been ablated and then we would be looking at a rocky core. And of course, our probability distribution does go down at the 90% level to objects that have 2 times the radius of the Earth. Okay, there we go. So here again is our probability distribution. And at this point, we were left with the question of, well, okay, we've established that this has all the characteristics of the passage of an object that has a well-defined surface in front of the X-ray source. We know the size of the object, we know its relative speed, but what is the object? And so the first thing we did is to think about objects that have sizes like this. And there are 2 classes of objects which are consistent with the entire probability distribution. They could have, there could be examples of them at any point in this probability distribution. Those are planets and white dwarfs. White dwarfs, however, are not expected at this age. They tend not to form until about 100 million years have passed. And even if they had formed, if they are in wide orbits, they would serve as gravitational lenses rather than obscuring the light. They would add to it. There would be an increase in light as the white dwarf passed in front of the X-ray source. So we eliminate white dwarfs. Now, what about brown dwarfs and M dwarfs? So here we have to look at the relationship between size, age, and radiation. So brown dwarfs, and this should probably say, and the lowest mass white dwarf, M dwarfs, correspond to the large radius, low probability, low entropy possibilities in our fit. At young ages and in a very substantial radiation field, they are likely to be significantly larger than their equilibrium radii. Now, the bottom line is, of course, we can't rule them out entirely. It's possible that they could be the thing that passed in front of the X-ray source, which is why we're calling M51 ULS-1b a candidate planet, right? But let me just say a few things about size, age, and radiation. If you looked at a 0.1 solar mass M dwarf, it would take about 50 million years to decrease its radius to 2 Jupiter radii. And in fact, what people who study M dwarfs find is that they can be larger than predicted by theory. Some of them are large, and we don't really necessarily understand why that's the case. Brown dwarfs are also born with relatively large radii. And of course, in this case, apart from age, we have the rather significant radiation field to deal with. Now, brown dwarfs locally, if they are in close enough orbits to transit, tend to be less well represented in the population of transitors than are either giant planets or low mass stars. Of course, we don't know if in the environment of M51, and in particular in the environment of this X-ray source, if the same thing holds. But it's another thing that makes us not jump to brown dwarf as a likely candidate, although mostly the reason is simply because it's only in a limited part of the parameter space that brown dwarfs would be allowed. So in summary, we have identified an event caused by the transit of a solid body in front of an X-ray source. This is a proof of concept. It shows that whatever this object is, we can find solid body objects transiting X-ray sources, even in external galaxies. The most likely radius of this particular accretor is comparable to that of Saturn, and the planet model is favored over other possibilities. So what we're saying is that this is an exoplanet because it's in another galaxy, and that this exoplanet should be thought of as a candidate planet. Now, what would be needed for confirmation? A lot of times people concentrate on needing to see it again, right? But In fact, we really know that this was a transit and that it had certain properties. If we saw it again, it would be wonderful because we'd have the orbital period. What we would love to do is to understand better objects at the low probability end of the probability distribution to see whether that end of the probability distribution is actually occupied by young brown dwarfs and young M dwarfs. So although these types of questions have been studied, they have not yet been studied in an environment that's as rich in X-rays and UV radiation. So that would be a great step of theoretical investigation. And also, of course, if we can find more of these observational, for observational benefit. Now, a very important component of future studies, particularly of this system, is the dynamics. So we really do need to treat this as a three-body system. A very interesting thing about the system, and any such system that other people find, is that its past and its future are fascinating. They're different from anything else we've studied in planetary systems, right? The donor will eventually fully evolve. Right now, there's a lot of mass loss. There may be another epoch of very heavy mass loss, this mass streaming past the planet. On the one hand, the mass loss may tend to make the orbit larger. On the other hand, there may be dynamical friction, which moderates that effect. There may be a supernova or a failed supernova. Eventually, the inner binary will be a binary of two compact objects, and we don't yet know if that will be two black holes, two neutron stars, or a combination. We don't know enough about the future of the planet to know whether it will be ejected or whether it will be able to stay. But if it stays, and if these two objects are close enough to merge in a Hubble time, that is the two compact objects, you have a planet that would be fairly close to a future gravitational merger. And if it doesn't survive to that point, one way that it might end its existence is through a tidal disruption by one of its companions. Now, these are just possibilities. In order to study them, we really have to open up a kind of a new field of study of planets within X-ray binaries. How do they form? How do they evolve during the evolution of the first star? And what happens to them during and after the evolution of the second star? My guess would be that if these massive systems start out with many planets, that the various fates we've discussed will be experienced by some subset of the planets. And it is possible, perhaps, that one of them would be like this system, and this system will either be ejected, undergo tidal disruption, or perhaps be present during a gravitational merger. So looking to the future, I think what we've done is we've demonstrated that these transits can be identified. And finding it in M51 corresponds to the discovery of a candidate planetary system in an external galaxy. The first was the first such. We used only archived Chandra and XMM data. And I think perhaps an important part of this is that by using the X-ray data in the way that we have, we were able to essentially jump over other methods to study potential extragalactic planets. I don't think the Decadal Survey had extragalactic planets on its list of things to be done this decade, although it was actually done before they finished the Decadal Survey. And I don't know when it would have been done, because it's something that we got to by following a kind of an odd side route. It wasn't our initial goal, but it was simply something that we noticed in the course of doing other research. Now, for this research, although we don't necessarily need new X-ray observatories, we would love to have links, because we would love to have the sensitivity and the number of photons that we could get from links. But whatever we have, modeling is of key importance because most dips are not caused by planets, right? Now, are we going to find more? Well, we've only looked at a very small fraction of the archive data. So just from that alone, we might expect that we should find more and our colleagues should find more. But of course, additional data will be important. In this talk, I have emphasized the search within external galaxies, but this can also be done in the Milky Way and the local group for any X-ray binary or any bright enough X-ray source. For X-ray binaries, the method complements other methods of looking for planets because it focuses on binaries in which the stars start out with high mass, and that's hard to get at in other ways. So I want to end by thanking a number of people. One of them is the group, the Chandra Public Affairs team of Megan, Peter, and Kim. They volunteered their assistance long before we had any idea that we needed their assistance. They were later joined by Nadia Whitehead. And of course, we all know that we have a wonderful library staff. And so I got an email just out of the blue from Maria McEachin last weekend telling me that she and her husband, Stephen McInerney, had found a novel that mentions that in 2255, the Winfield telescope will become operational and is expected to provide the first glimpse of extragalactic planets. So thank you for that. And the other news from that year is also interesting. The Kennedy Space Center was reclaimed, and it sounds like there's going to be a museum of things that launched from there. And watch out for those anti-grav belts. So thanks very much, Maria, for this. And then finally, we end with the team that, everybody had a role to play in making this happen. And it was a wonderful team with which to work. We helped to get each other through the pandemic, I think. And we are now being joined, for some reason that last, there is a last one here that shows that we're being joined by some people. And rather than let it be mysterious, I'll tell you, we have a high school student from India who's worked for a year and a half on this, Samarth Kumar. We have a student from Boston College, Zakai Zhang, who recently joined us. Sylvia Tunin and Fleur Brokarden are going to be working on the three-body problem. And I'm sure I've left some people out, but everybody, it's a relatively small group to be doing this work, and everybody has played an important role. So I want to thank them and thank you for your attention.
Thank you very much, Roseanne. That was a wonderful talk. So this is now open for questions. And I know this takes people a moment to get organized. So they will ask questions by raising your hand. Oh, we've already got the first one. So Arjun and or Joe.
Hi, Roseanne. That was really a wonderful talk. This is Arjun Jones here as well.
I recognized your voice.
I wanted to ask the astronomer question, since you found one out of how many ever you looked at. What does this tell us about the population of such planets around X-ray binaries?
Well, as you well know, we should really be careful using our statistics of one, right? So, nevertheless, in our paper, we did do a statistical analysis or a probability analysis. And honestly, I will be completely honest and say, if all we were looking for were planets, we knew the probability was so low that we probably shouldn't be looking. So we were actually hoping to find a bunch of different things. But the probability is low, both because it goes according to the time you have looked divided by the orbital period. I actually have a slide on this. Here we go. And if this is a very wide orbit, that's small, but even smaller is the geometrical factor. So the wider the orbit, the smaller the probability. And if the orbit has a random orientation, the probability is on the order of 1 in a billion. And I don't think it's telling us that the number of planets in X-ray binaries is really that large. So we have to understand it, because we do expect to find more. If you just go by the argument that we analyzed a very modest amount of data, and there's a lot more data out there. One thing that we did find, and this was one of the things that made me want to look at this more. Remember, we had sort of put this aside for a while. Ryan discovered this, both in XMM and in Chandra, you can see evidence of an eclipse. In this case, an ingress into the eclipse, and here from Chandra, an egress. Now, we know that there tends to be coplanarity between binaries and planetary orbits when you find planets in binaries. In this case, though, you can argue this any way you want, because you probably had a supernova before. If you were coplanar to begin with, would you continue to be coplanar? Would mass transfer perhaps tend to establish coplanarity if there wasn't coplanarity to begin with? So I think our knowledge of the science allows us to argue this in any way that you'd like, and there are reasonable arguments on all sides of this issue. All we can say is that we found it. And the fact that we found it means that they can be found. If it turns out that the fact that this is eclipsing was important, then when more are found, we'll see whether they are more commonly found in eclipsing systems. If that's the case, so that coplanarity holds at least some of the time, then the probability argument is not so terrible, and you might come up with numbers on the order of 10 per system. But you should look at our argument, which you can tear to pieces if you'd like, but we felt that we had to make it because, in fact, this is, on the face of it, a low probability thing to happen. And yet, from the data, we're certain that it did happen.
Okay.
Thanks. That sounds very optimistic.
I hope so.
Okay, we've got more questions. Steve Wilner.
Hi, Roseanne, this is just fascinating stuff. On that slide that you showed all the light curves, I don't know, a dozen or so from top to bottom, the bottom one had a big dip in it at the very beginning. And
That's
is
right,
that
yeah.
what you were just talking about, or is that something different?
Let me just go back. Oops,
There you
there
go.
we go.
Yeah.
Yeah, that's right. That's an eclipse. Mhm.
Okay. Thanks.
And you can see here, now you might wonder why there's so many eclipses, because you can also see the ingress to eclipse over here, right?
Right.
And here you have what looks like a full eclipse. Well, the neat thing about X-ray binaries is that they're either Roche lobe filling or close to it. So the donor star has a certain radius, and the distance between the donor star and the accretor, if it's Roche lobe filling, is typically only a few times larger than the radius of the star. And if it's not filling its Roche lobe, it still needs to be pretty close in order for there to be significant accretion. So therefore, the ratio of the radius to the distance is much larger than it is in typical binary systems. That's a good question.
Okay, thanks.
Okay, next question from Pepe or possibly Martin.
Martin in this case. Hi.
Hi.
Suzanne. I was wondering, in the as you move this occulting disk across the accretion disk, whether you get the consistency with the simple alpha disk, because the temperature should be rising towards the center, and then.
Oh, you're far more sophisticated than we were.
I doubt it. I doubt it.
All we did was to assume it was optically thick. So we had an optically thick object, which a planet would be, right? Oh, I see. You mean the object? You're talking about the source.
You have this black disk.
No, we did not model the source that way.
But that could be a fun thing to try.
It could be. And in fact, next week, I'm going to be giving a talk on Friday, what did they call it? The ADR Act, where I'm going to be talking about gravitational lensing in binaries. And there, the very point that you raised is of crucial importance, because there you actually get finite source size effects as a black hole lenses a black hole companion that has a disk, and you can learn about the disk through that. Or alternatively, if you know about the disk, it tells you something about the size of the Einstein radius and therefore the mass of the lensing black hole. So it's very, very relevant in that case where you're getting a lot of light. In this case, the light disappeared and came back again over 3 hours. So, you know, we didn't have a lot of photons to fool around with, you know, on an ingress or egress.
Okay.
Well, from the same household.
I can see that. Is Elizabeth with you, by the way?
Oh, not today, no.
Everybody else, I'm talking about Elizabeth Warren, who lives nearby.
Yes, she does. Anything you can say about the atmosphere of this planet?
Maybe that's a fantastic question. Because as you know, in studying transits, right, optical transits, people have done wonderful things to learn about the atmosphere. In this case, we have far too few photons to do that. But I would anticipate that, you know, particularly if we get missions like LINX, and particularly if we're able to study systems that are nearer to us, that we would be able to see what's happening as the atmosphere of the planet passes in front of the X-ray source. And then, you know, this would give us the kind of stuff that people get from the accretion-related dips, which I see Josh here. He studied. He was a co-author on the paper that I showed, where you'd actually begin to get some information, chemical information. But we're very far from that in this particular project. You know, this had a count rate of about 10 per kilosecond.
Okay, thanks. John, I think you have your up next.
Hi, Roseanne. That was really interesting. Mine is a pretty similar question. Hot Jupiters tend to have exospheres that are several times larger than the planet. And they absorb soft X-rays much more effectively than hard X-rays. So the question is how hard this source is, whether most of the photons you're seeing are like 1 keV or 2 or 3.
Yeah, now that's a good question. Because this is a soft source, really most of the photons are below 2 keV. So we don't have the ability to do relative studies. So when we're looking at hardness ratios, we're looking at the ratio of the numbers of counts in one very low energy band and another band that many people would also consider to be a low energy band, right? So that's the property of this source. What I will say is that on the one hand, that property of the source limits the ability to do what you were talking about. On the other hand, the fact that it was a thermal spectrum meant that we were able to get an effective radius. And so in some sense, this was almost too good to be true, right? That just in the kind of source where you can estimate, even though it's only a kind of a crude estimate, but you can estimate the size of the source. Did we happen to see an object that passed by that had a size very comparable to the source? But the downside is that we couldn't really do that kind of spectral analysis.
Okay, thanks.
Okay, Josh. Up, you're muted, Josh.
Should have remembered that. Okay, very nice talk, Roseanne. I'm surprised. This is a superluminal source, an M51, right?
That's right. It's well, an ultraluminous source.
Ultraluminous source, yeah, whatever way we want to call it. The ones that have been discovered, and Fiona and New Star have played a role in this, have typically been pulsars. They're with very, very high magnetic fields. They're not magnetars. These are very luminous sources. Otherwise, we wouldn't call them that. And so in that case, I'm wondering why your whole picture here is talking about the X-ray source as a predominantly disk system, because if it's a accretion onto a neutron star at Eddington rates, it's something very different.
Right. Now, in fact, we didn't talk about it primarily as a disk system. This seems to be an optically thick object which has a spherical photosphere, right? At least that's what we get from looking at the effective temperature. Now, as you know, when you have more photons, you sometimes learn a lot more about what's going on there. But we did not treat this as a disk. We just treated it. Our treatment was very simple. It was a disk that was emitting X-rays. that was the extent of our treatment of it. But you're right that in other cases, it's almost a trade-off. And it'll be very interesting to see. I'm hoping that other people and we as well find additional examples of this.
Mhm.
Some of them will be in systems that are quite different. They'll have harder spectrum, they'll be disk dominated. And there the analysis could, on the one hand, be more complicated, and on the other hand, give us more information. In fact, I actually have, I thought people might ask about microlensing planets. There's a feature about microlensing. Remember, I said that you find these simple light curves, you find the light curve shape and you find the spectrum, right? But there's actually a lot of information when you have anomalies. And that's how we learn about things like planets, finite source size, binarity, and so forth. So I think the same thing is likely to happen with transits. I think we looked for the best example of something that was the simplest possible transit. Because I don't think you would have believed us if we came in with some kind of weird shape dip, right? You'd have lots of reason not to believe us. So it's just like with microlensing, when you're establishing that you can find them, I think it's important to really stick with the basics and find things that are almost incontrovertible examples of what they are. But eventually, if this is successful over the long term and people find more of them, we will be able to do the type of thing that you were suggesting and that Martin and Pepe were suggesting and John, and really learn more about the systems.
Mm-hmm.
And we'll be forced to do more complicated modeling. Give us links. That'll certainly help.
Okay, well, a very lively conversation. I don't see any further hands. And we just hit the top of the hour. Oh, one last one. So Arnold will get the last question.
Roseanne, I was just wondering.
Hi there, Arnold.
Hi. I was just wondering, I assume this source does actually is present in the Chunder source catalog. And have you looked at the variability parameters in the catalog, and would that be possibly grounds for doing a search across the entire catalog?
Absolutely. I think Pepe took me to task for not doing that. But actually, Raphael, who, as you well know, is expert on this, has started looking at this, the question of looking for anomalous sources in the catalog and identifying possible transits that way. So far, that hasn't led to a definite result. So what we're doing, of course, is I think that's an important thing to do, and we should be doing that, and we should be doing it more aggressively. And we also are upgrading our search routines so that we find not only these excellent examples, but just to be aware for ourselves of what else is there, even if it's not time to publish them, even if they need more analysis, just to get an idea of what else is there. So there are lots of upgrades, and certainly this is an excellent suggestion. The catalog, certainly the catalog contains all the examples that there are of X-ray sources with planets orbiting them. So if we had a simple way to analyze at the level of the information in the catalog, that's a great gift.
Okay. Well, thanks very much, Roseanne, for a fascinating talk, and I have to say a very lively discussion. So thanks to everyone for that. And Roseanne, of course, will be here, as she has been for some time. And I highly encourage you to talk with her, email, and hopefully someday soon we'll all be meeting in person.
Great, great. Okay, thank you, everyone. It would have been great to see you all in person.
Thank you.
Okay, bye-bye.
Bye.